Okay, so let's continue our discussion related to the second module of this particular course on semiconductor devices and analog circuits. So today, in the last lecture, we saw there was an introduction to semiconductors, and today let's look at p-n junction diodes in brief. So before that, in the last lecture, we had seen that semiconductors, one of the ways of altering the properties of a semiconductor is through a process of doping. So if we have a semiconductor such as silicon, and if we add an impurity from the fifth column such as arsenic, then these let the number of arsenic atoms, we call them as donors because they donate electrons to the conduction band. So what happens is these arsenic atoms, they get ionized, positively charged, and they donate the electron, and this electron goes to the conduction band. And so the electron goes to the conduction band, and number of electrons in the system then are practically equal to the number of donors. And in equilibrium in semiconductors, we have this relationship that the number of electrons multiplied by number of holes is a constant equal to Ni square, and Ni square is a constant at a particular temperature. So for silicon, Ni is 1.45 into 10 to the power 10 per centimeter cube at room temperature, T equal to 300 Kelvin. And so what will happen is that each arsenic atom will donate an electron to the conduction band. And so if we have let's say a typical donor density, Nd equal to 10 to the power 16 per centimeter cube, then the number of electrons will be practically equal to the number of donor atoms that you've added here. Nd equal to 10 power 16. And note that if you don't add any impurities, and if the semiconductor is pure, then the number of electrons is equal to number of holes equal to 1.45 times 10 to the power 10 here. And when you add 10 to the power 16, so there are some electrons and holes in the background because of this thermal generation process. But when you add an impurity, which is 10 to the power 16, 6 orders of magnitude higher than this here, number of electrons is practically equal to the number of donor atoms that you've added here. So N equal to 10 power 16. And then we have this relationship, N into P is Ni square. So P goes down, Ni square by N. So this gives us 2 times 10 to the power 4. So, so in a semiconductor like this, where number of electrons is much, much larger than number of holes, we call such a semiconductor as an N-type semiconductor. An N-type semiconductor. And the picture that we have is in this N-type semiconductor, we have these positively charged donor atoms. And these are the donor atoms like arsenic or phosphorus. Since they have lost an electron, they are positively charged. And we have lots of electrons in the system, almost equal to the doping density here, the number of dopant atoms that we've added here. So the number of electrons is practically equal to 10 power 16. Note that although the electrons have been shown close to the positively charged donor atom, the electrons are free. These electrons are in the conduction band. They're free to move in the lattice. Okay, so that's a N-type semiconductor. And what we are seeing, and this is a point that we emphasized last time also, that very small amounts of impurity results in large change in the conductivity or the resistivity of the silicon sample here. So number of silicon atoms per unit volume is about 5 times 10 to the power 22. And we just considered a case where we added 10 to the power 16 donor atoms, donor impurity. So the ratio of donor atoms to the total number of atoms is 2 times 10 power minus 7 here. So this is 0.2 parts per million. So that's the concentration of the impurity that we've added to the lattice here. So very, very small amounts of impurity we've added, donor atoms we've added. And the consequences are, we're just giving you the number here. The consequences are, if I take intrinsic silicon with no impurities at all, the resistivity is 2 times 10 to the power 5 ohms centimeter here. And when I add 10 to the power 16 donor atoms, the resistivity drops to 1.5. So what is being emphasized here is, look, there's a 5 orders of change in the resistivity. 5 orders of change in resistivity through very, very small amounts of impurity, 0.2 parts per million here. And that's an important characteristics of semiconductors, that you can alter their resistivity or conductivity by such large orders of magnitude through very, very small amounts of impurity, right? So you can't do that, for example, in a metal. You can't change the resistivity of a metal by orders of magnitude like this. And neither can you alter the resistivity of an insulator. But semiconductors allow you to modify the resistivity in this particular manner here. So p-type semiconductor, we add, as we discussed, a group 3 element such as a boron. And what this group 3 element such as a boron does, let the concentration of these boron atoms be Na, number of acceptor atoms. And you're seeing why we call it an acceptor atom, because it accepts an electron from the lattice and gets negatively charged, and thereby it creates a hole. It creates a hole in the valence band here, right? And so, and it's for that reason that we call such an impurity as an acceptor type impurity. And if the concentration is Na is 10 per 16, so what would happen is the number of holes in the system would be practically equal to 10 per 16. And the number of electrons would be Ni square over P. This P into N is Ni square relationship holes at equilibrium. So N is Ni square over P. So Ni square over Na about 2 times 10 per 4. So by adding 10 to the power 16 acceptor atoms, what we have done is we have made number of holes in the system P much, much larger than number of N. And we will call this semiconductor as p-type semiconductor, because P is much, much larger than N. And the picture that we have is that all these acceptor atoms that you see here are all negatively charged. They're all negatively charged because they've accepted an electron from the lattice, so they're all negatively charged. And they've created these holes, and the holes are free to move in the valence band. They're not confined to a particular atom or a particular place. They're free to move around in the lattice here. So that's the picture of the p-type semiconductor that we have. Okay. All right. So the number of carriers, for example, if I were to take an n-type semiconductor. So we've said that this n-type semiconductor will donate n-type impurity or donor impurity will donate an electron to the lattice, and the number of electrons will be equal to the number of donor impurity, which is true over a particular temperature range. Now, if you go to lower temperatures, what happens is that this electron, that extra electron that arsenic had, doesn't have enough energy to get free from the arsenic atom. And therefore, it stays with the arsenic atom, and therefore, this particular electron doesn't go to the conduction band as temperature is lowered. And this is what we call as donor freeze out. The electron stays frozen onto the donor here. And so then the number of electrons reduces as you go to, note that this is 1 over T. So as you go to lower temperatures, the number of electron reduces because arsenic, there's not enough thermal energy to separate the electron that is attached to the arsenic away from it and take it to the conduction band. On the other hand, when you go to higher temperatures, what happens is there's a normal thermal generation process through which electrons and holes are created. So that process becomes very significant, and the number of electrons starts increasing because the temperature is so high that the number of electrons created through thermal generation process becomes larger than the number of electrons, let's say, that come from the arsenic here. So in general, the number of electrons versus temperature follows a graph like this here. And so this is the normal range in which we work. We don't want to go to lower temperatures because then the number of electrons is falling. We don't want to go to higher temperatures also because again, the device is very sensitive to temperature. And when most of the carriers come from thermal generation, the semiconductor is no longer NOP because thermal generation creates equal amounts of electrons and holes. So the semiconductor behaves like intrinsic. So in here, if you take an n-type semiconductor and you raise its temperature to a high level here, and if you're somewhere here, the n-type semiconductor is practically behaving like a intrinsic semiconductor in the sense that number of electrons and number of holes are equal. Why? Because most of the electrons and holes here, they come from thermal generation process. It's only here that most of the electrons come from the donor atoms and the material is n-type. And here, the impurity is not able to, is inactive here, so it's not able to create release electrons to the conduction band. So the process of doping is failing over here. So this is the temperature range in which our semiconductor would behave as an N-type. Okay. So the consequence of this is that there's a range of temperature within which, if you're going to make a semiconductor device, let's say a p-n junction, the p and the n region will stay as a p and n over a temperature range only. If you go to lower temperatures, you have these freeze out problem. If you go to higher temperatures here, you have a problem of a lot of thermal generation occurring and the semiconductor losing its n-type or p-type character. So coming to current flow, there are two mechanisms due to which current can flow. One of them is what we call as the drift current due to electric field. And so the idea is something which is familiar to us, that if we apply an electric field like this, the electron carries a negative charge, so it will start moving in the opposite to the direction of the field, and the movement of the electron will contribute to current, and we call that as the drift current. The electron begins to drift. Note that the electron normally is moving around randomly, and there's no net motion of the electron. But when you apply an electric field, the electron acquires a net motion opposite to the direction of the field here, and we call that the electron is drifting opposite to the direction of the field. And whenever there's a net movement of charge, we know there is a current. So the resulting current is called electron drift current. Similarly, the hole being positively charged particle, so the hole will move in the direction of the field, and we call the current, resulting current, as the hole drift current here. So these are due to the process of electric field here. Now, electrons and holes can also move even though there may be no electric field. For example, if there's a concentration gradient. So P denotes the hole density as a function of X, N denotes the electron density as a function of X. So let's say the hole density goes like this here. The hole density reduces with position in this particular manner here. And we know diffusion, the holes will try to go from higher concentration to lower concentration. So as a result of this gradient, the holes will try to move from left to right, and any movement of charge will give rise to current. So we have something called hole diffusion current. On the other hand, if electrons decrease like this here, the electrons will also move from left to right here because of diffusion, but because electrons carry negative charge, so there would be an electron diffusion current from right to left here in this direction here. So there are two separate mechanisms due to which current can flow. One of them is the electric field, and we call that current as a drift current. The other one of them is due to concentration gradient, and we call the resulting current as a diffusion current. There's another interesting phenomena that occurs in semiconductors, which is recombination and generation. Okay, so there should be a slash here, recombination, generation here. So let me illustrate. So we have electrons here in the conduction band, and you have holes in the valence band here. So it can happen that while the electron is moving around, let's say it's moving around, the electron may find a hole in the neighborhood, and the electron may fall into the hole here, and thereby the electron is gone and the hole is also gone. So you've lost one electron hole pair, and we call that process as recombination. The electron is recombined with the hole. Similarly, the hole could be moving here. The hole may find itself in the neighborhood of the electron, and the electron may fall into the hole here, and you've lost an electron hole. So this is what we call as a recombination. So recombination is continuously occurring. When you have both electrons and holes, the electrons and the holes are recombining with each other. But there's an opposite process also. Because of thermal generation, note that you have thermal generation will take an electron from here and promote it to the conduction band, and thereby you get a electron hole pair. So similarly, electron hole pairs are being created also. Electron hole pairs are being created also through thermal generation. So there's recombination occurring, there's generation occurring, and in equilibrium, the two processes, they balance each other, and we have a stable concentration of electrons and a stable concentration of holes. So recombination generation is also an important phenomena that we need to keep in mind while trying to understand semiconductors. All right, so with this background, let's go on to the p-n junction diode. So p-n junction diode, the symbol, we are well familiar with the symbol of the diode here. And this side is what we call as the anode, and this side is what we call as the cathode. And this is the structure of the p-n junction diode, simplified structure that we often draw We denote the anode as P and the cathode as N here. And these are the two electrodes that are there. So there's a P-type region and there's an N-type region. But the actual PN junction is not like a bar that you see here, but it's more like this here. That this is a cross-sectional view of a semiconductor. Let's say the semiconductor is normally N-type. And what you do is you create a region which is P-type in this particular semiconductor here, P-type here. And you make a contact here and you make a contact here. And how do you create a P-type? By diffusing P-type impurities such as boron into it. So as an example, one could have a semiconductor silicon with a N-type doping of about 10 to the power 16 per centimeter cube. And then we may add 10 to the power 17 boron atoms. So what happens in this region, there was this donor atoms 10 per 16, but we've added 10 per 17 boron atoms. So they compensate the effects of the donors and the region becomes P-type here because the boron atoms are much more than, let's say, the arsenic atoms which are present here. So this region becomes P, this region stays N, there's no P-type impurity here. And so we get a PN junction here. So when we are drawing a diagram like this, what we are talking about is a diagram which is within the dotted lines here. We are showing only a part of the structure here, but PN junction is more, has several other parts here. So this is a more realistic picture of what the PN junction diode looks like. All right, let's look at its operation. So for the sake of discussion, let's take a P-type region with a doping of acceptor type doping of 10 to the power 16. And for simplicity, let's take a N-type with a donor density of 10 to the power 16 also. All right, so then the picture that we have is of this PN junction diode. This P region will have all these ionized acceptor atoms that you see here, negatively charged acceptor atoms, these big circles that are there here. And you'll have a lot of holes. Every acceptor atom will create a hole. So you have all these positively charged holes that you see here. And there'll be very few electrons in this particular system here. So for example, we've already seen if you dope 10 to the power 16 doping density, then the number of holes will be equal to 10 power 16, and number of electrons, we are giving only order of magnitude, is 10 to the power 4. So that's why in all this lot of holes, we have shown only one electron. And because the ratio is, you can see here, the holes are much larger in numbers compared to the number of electrons. So that's the picture of P-type that we have here. And the picture of N-type is just complementary. We have all these donor atoms which are positively charged, and we have all these electrons that are there, and maybe, you know, very few holes that are there here. N equal to 10 power 16 and P equal to 10 power 4. So let's imagine that the P-type region and the N-type semiconductor are brought together just to understand the behavior of the PN junction, or how it would act if the two regions are brought into contact with each other. So let's see what happens. So when we bring them together, note that there are lots of holes in this particular region here. And you can see all these holes, positively charged holes here. And you have all these very few holes. So we just saw that there's a huge concentration gradient in the hole density here. And therefore the holes will tend to go from P to N. Because of the concentration gradient, because of the diffusion process, the holes will tend to go from P to N. Similarly, you see all these electrons that are there here. So many electrons in this particular part here. And there are very few electrons here. So there's a huge concentration gradient in electrons. So the electrons will try to move from N to P here. And the donor atoms that you see here, they cannot move because they are fixed in place. They're fixed in the lattice. They're heavy and they cannot move at the normal room temperature. Similarly, acceptor atoms are also immobile. Compared to the electrons and holes, these are immobile at normal temperatures. Okay, and so the acceptor atoms are fixed, the donor atoms are positively charged, donor atoms are fixed, so they stay in place. But electrons and holes are mobile carriers, so they will move, and holes will move from left to right, and electrons will move from right to left here. So let's do that. Now the moment an electron comes here, it leaves the N region and comes to the P. What this electron does is it finds itself amongst lots of holes there. And you can see that the electron will find itself in the neighborhood of a hole. And we just saw when an electron and a hole get close to each other, they are in the neighborhood of each other, recombination occurs. And so what happens is an electron left this place, came here, and there are lots of holes here. So the electron recombined with the hole, and both of them are lost. So both of them are lost. The hole, for example, may diffuse to this side. The hole finds itself amongst lots of electrons here. The electrons and the holes recombine, and the electron hole pair is lost. Now note the consequence. Beforehand, if we go back here, beforehand, there's an electron and there's a positively charged donor atom. So the electron is compensating the positively charged donor atom. So the overall, this region is neutral. Similarly, this region is neutral. There's a negatively charged acceptor atom. There's a positively charged hole. So these are all neutral regions here. Even though charges are present, but overall, you can see that there is neutrality there. But the moment that this happens here, this electron goes here and this one here. So now an electron which was compensating this particular region is lost. So this particular region will become positively charged. A hole which was compensating the negative charge here, the hole is also lost. So this region becomes negatively charged. So the regions start getting charged up. Note that when it goes here, this region here will become negatively charged. This region will become positively charged. So as this happens here, you can see here that the region here, see, electrons will move from close to the boundary here, and so these regions will first start getting charged up. They have lost their electrons. These regions have lost their holes here, so they start to get negatively charged here. Now, because of this positive charge and negative charge, an electric field develops here with the direction shown here. And note that the holes were trying to move from left to right through because of concentration gradient, but the holes begin to see an electric field now. And electric field, the direction of the electric field will tend to oppose the movement of holes here. So now there are two processes occurring. The holes will like to go to the right because of concentration gradient, but the electric field is opposing. But the electric field is not very strong, so the holes still go to the right and the electrons still come to the left here. So that process still occurs here, right? So this process still occurs here. But now what happens is there are more charges in this particular place. So this occurs here. So the electric field becomes stronger, and the electric field becomes stronger and opposes the tendency to diffuse to the right here, of the holes to diffuse to the right and electrons to diffuse to the left here. Eventually, you can imagine that what happens is that the two processes balance each other. The tendency of a hole to move to the right to the N region because of concentration gradient is balanced by, is opposed by the electric field here, which tries to push away the holes and causing them to remain in the P region here. And when the two tendencies, when the two effects cancel each other, we reach the equilibrium condition where there's no net flow of carriers across the junction. Okay, so no net movement of carriers. But what has happened in the process is that in this particular region, close to the junction here, the junction between the two P and the N regions here, close to the junction, we have lost holes. We have lost holes from here, which went over on the N side and recombined, or electrons came over here and recombined with the holes here. So we've lost holes from this particular region. We have lost electrons from this particular region, leaving behind positively charged donor atoms and negatively charged acceptor atoms here. So what we end up is basically in equilibrium, there's a region which has lost its electrons and lost its holes here. And we call this region as a space charge region. And the reason for calling it space charge region is very simple. It's a region in space. It's a region in space where there are charges, right? There are positively charged donor atoms here, negatively charged acceptor atoms here. We call it space charge region. Another common name for it is what we call as depletion region. So this is a region where the number of which has lost its electrons, or this is a region where it has lost its holes here. So it's depleted of holes here, depleted of electrons here. So in general, this particular region is depleted of carriers. Not that the carriers are zero, but a lot of carriers from this particular region have recombined and gotten lost. So we call this region as depletion region here. Okay. Outside the depletion region, the N region is as it is, and the P region is as it is. So these are all neutral regions. There are no net charges here, no net charges here. But here, there is a net positive charge here, there's a net negative charge here. So that's where you have electric field and all these things that are there here. Okay. So note that, again, I want to emphasize that although small, depletion region has carriers here, because note that this region stays as it is. So this is still a p-type region with 10 power 16 holes and 10 power 4 electrons here. This region has 10 power 16 electrons and 10 to the power 4 holes here. So we look at hole density. So hole density starts from 10 to the power 16 and eventually goes to 10 to the power 4. And so, it's 10 to the power 16 here, and then as you enter the depletion region, it becomes 10 power 15, 14, 10 power 13, 10 power 12, 10 power 11, 10, 9, 8, 7, 6, 5, and then eventually 4. So the hole density is reducing from 10 to the power 16 to 10 to the power 4. As you enter the depletion region, the hole density is reducing here, eventually reaches 10 power 4. Similarly, electron density starts from 10 power 16 here and reduces sharply to 10 to the power 4 here. So there are electrons and holes in this particular region. But if we look at the concentration of holes, the concentration of holes is much smaller than the doping density, number of acceptor atoms. The number of electrons is much smaller than the donor density. And so number of holes is smaller than number of holes here. Number of electrons here is much smaller than number of electrons here. So that's why we call this depletion region here. All right, so because of the electric field, you can imagine if there's an electric field from here to here, note that the regions outside are neutral. Then there is a potential whenever there's an electric field. So if you integrate the electric field, you will get a potential here. So what happens is that when you bring P and N region here, this depletion region forms, and this electric field, because of the charges, electric field is present, and there's a potential here. So this is just a schematic illustration of potential. And we call this potential as the built-in potential. This potential is not due to some external voltage that has been applied, but as a result of movement of charges from left to right and right to left, movement of electrons and holes, that these charges have come about because of recombination process here. So this is an internal electric field, and this is an internal voltage here, and we call it built-in voltage here. It is built into the PN junction. It's not something which is external to it. And we can show that the built-in voltage is equal to, this is Boltzmann constant, temperature in kelvins, kT by Q, ln Na Nd by Ni squared. Ni is the intrinsic carrier concentration. And so we can calculate the value kT by Q, Boltzmann constant T by Q at room temperature 300 degree Kelvin. This particular value is 26 millivolt. 26 millivolt, and if you put in these numbers, Na and D 10 power 16, Ni is about 1.45 times 10 power 10, you get a value of VBI equal to 0.86, a typical value of the built-in voltage here, right? If the doping density were less, it would become maybe 0.75. Note that it is log of doping, so it doesn't change so drastically with doping because of the log function here. And VBI will be typically less than 1 volt, and somewhere between maybe 0.7 or 0.9, 0.95, depending on the doping that we have on the two sides here. Okay, so there is a built-in voltage inside the PN junction, this electric field there, and the presence of the electric field or the potential here is what is preventing the carriers from moving from one side to the other side. So note that there are holes here. As we said, there are holes here, and they would like to move because of the concentration gradient to the N side. But note that the hole will see a potential barrier here. The hole has to, it has to surmount this potential barrier to come to the N side here. And similarly, the electron sees a potential barrier here. So the electron, so either you can talk in terms of electric field, that the movement of holes from P to N is being opposed by electric field, or you can say the same thing, that the hole actually sees a potential barrier here, a barrier of 0.86 volts. So the hole needs to cross this particular barrier to come this particular side. The electron also sees a barrier of 0.86 volt here. So this barrier, potential barrier, prevents movement of holes and electrons due to the concentration gradient. Now this is we can show that anytime you take two materials, it's not just about P and N. In this case, when we took P-type and N-type region and we brought them into contact, we're finding that there is a potential that develops at the junction. Now that is true for whenever you bring two different materials into contact, you will find that a potential develops between them. And that potential is what we call as the contact potential. And that's because of, whenever you put two different materials in contact with each other, there's an exchange of charge, electrons and holes. Even if you take two metals, electrons may flow from one side to the other side. And because of what we call as the work function difference. And because of this exchange of charges, there'll be electric field. And because of electric field, there'll be potential here. So this is a very general result. The value of built-in potential may vary depending on which two materials we are talking about. But in general, whenever you bring two different materials into contact, there will be a potential difference. That's a general result here. So coming back to this, so the picture that we have about p-n junction in equilibrium is, we have this p-type region, which is like a normal p-type region with acceptor atoms and holes here, and it's neutral. And we have n-type, which with donor atoms and electrons, and it's also neutral. But close to the junction, we have charges present here. And we said this is what we call as a depletion region. And again, we are not going to derive these things. That would be discussed in future courses. But if you're wondering how large is the depletion width, we can give you an expression for depletion width. Again, everything at equilibrium. So depletion width can be written as 2. This is the permittivity of silicon. We are talking about silicon p-n junction. Q, of course, is there. Na, doping of acceptor atoms, doping of donor atoms, and built-in voltage here. And built-in voltage, we've already given an expression. So if we plug in all of this, 11.7 is the dielectric constant of silicon. This is the free space permittivity. And Na and D, we are taking 10 power 16. So we get W of 4300 angstrom here. So 4300 angstrom or 430 nanometer or 0.043 microns. Okay, so maybe half a micron or so is the depletion width here. And if you're wondering how large is my p-n junction, so p-n junction itself, these regions could be hundreds of microns here and hundreds of microns here, okay? Or depending on how it is constructed, this may be a few microns, this could be hundreds of microns, depends on how it is constructed. Depletion width is fairly small. You can see less than half a micron here, 4300 angstrom, so less than half a micron here, okay? All right, so that was p-n junction in equilibrium. Now we have to use p-n junction, so we're going to apply voltages to it. And there are two distinct ways in which we can apply a voltage. We can apply a voltage by making p side with a higher potential compared to n side here by connecting a battery like this here. And we call this as a forward bias condition here. Forward biasing of the p-n junction. Or we could make the n region at a higher potential compared to p, and we call that the reverse biasing of the p-n junction. And all of you know that in forward bias, the p-n junction starts conducting current, and reverse bias, there's very little current. So let's look at how this happens here, okay? So this is a actual diode 1N4001, practical diode whose characteristics were measured. And this is what is shown as the characteristics of this particular diode. So this is, when we call this as positive here, it means that the p-type is bait, positive with respect to n. And so it's forward bias. And reverse bias is over here. And it seems as if the current is 0 in reverse bias, but that's because on this particular scale, you can't really see it. The current is small, and because it's so small, it's appearing to be 0. It is not 0, but some small value here, which we'll see later on. And the current also stays small and then, begins to increase rapidly. We'll come to that. So this kind of a behavior you see. So it's an exponential characteristics. So in the forward bias direction, the p-n junction has an exponential current voltage characteristics, and an exponential on a linear plot will look like this here, okay, and with this kind of a behavior. So p-n junction conducts significant current in the forward bias direction here, and in the reverse bias direction, very little current here. So that's the nature of p-n junction here. So forward bias, let's look at what happens here. So this is the picture that we have. We have depletion region, and there's an electric field in the depletion region. We said the other way of thinking about it, there's a barrier here, built-in voltage, VBI, and this electric field or the barrier is preventing holes from going over to the N side, electrons from coming over to the P side here. So when you apply a forward bias, so what would happen is this additional bias that you create, that will create its own electric field, right? You have positive voltage here and 0 here. So that will create an additional electric field on top of the internal field here. So the net effect is that the field will become smaller. The effective field will become smaller, and the depletion region will show you later on. The depletion region will become narrower. The lower electric field means less charges, so it will become narrower. The potential barrier that was there earlier equal to VBI is no longer VBI, it becomes less. And now the equilibrium has been disturbed. Earlier, the diffusion tendency was balanced by the electric field. Now the diffusion tendency is still there, the holes will like to diffuse, but you have reduced the electric field. So the balance is disturbed and current starts to flow. Now if you look at the bias, the way bias has been applied here. So when you apply a bias, of course you're expecting current to flow in this direction, from positive to the ground here. So you want current to flow in this direction. The battery requires current to flow in this direction. And so basically you're asking holes to flow in this particular direction and electrons to flow from this particular direction. Because this particular kind of a current would require holes to go like this and electrons to go like this here, right? Then only if electrons move in this particular direction, then only you will get a current in from left to right here, right? So this positive battery will require current like this here. So you're asking electrons to flow like this to contribute to current. You're asking holes to flow like this to contribute to current, which is fine. There are lots of holes here, and you're asking holes to go towards the N side, which is fine. You've reduced the electric field, so holes try to go towards the N side and contribute to current. You're asking electrons to go over to the P side, and the electrons would like to come to the P side because of concentration gradient, but electric field was preventing it. But electric field is smaller here. Electric field has been reduced, so the electrons are able to spill over to the P side here. So the current begins to flow. Okay, and that's what we were saying. The earlier these black dotted lines. So earlier the voltage was VBI. Now when you apply a forward bias, the electric field is reduced. The depletion width is now only in this narrow, the red dotted lines show the depletion width. And the barrier now is no longer VBI, but the barrier becomes VBI minus VF. Whatever is the voltage that you apply, it goes and is dropped across the depletion region here. So it becomes VBI minus VF. So that's the picture that we have. So that's why we are saying the application of forward bias reduces the barrier. The barrier of VBI to movement of holes from P to N side now becomes VBI minus VF. It becomes a lesser barrier. So that's why holes are able to cross over to N side. And same thing happens to electrons. So the mechanism of current is now what happens is, because of the reduction in electric field, the holes get injected into the p-type. See, the hole gets injected into the p-type. And the moment the hole comes into the injected into the n-type here, in the n-type it finds lots of electrons that are there here. So it will recombine there. Now, so recombine, so how does the current flow? So note that there's a movement of positive charge from here to here. So internally we can see current flowing, right? So from here to here, any movement of charge that is there. But how does the current flow in the external circuit? So when a hole goes over here and gets lost here, an electron hole pair is generated at this particular point here. And so what has happened is this hole that went over to this side, the number of holes is replenished. This extra hole comes in here. There was an electron lost from here. So there's a generation process. Let's see here. This electron then comes over to this side here. And so you're back to the same number of holes, same number of electrons, but an electron has moved like this here, from here to here into this particular circuit, thereby contributing to current, which is in this direction here, from positive to negative here. Similarly, what may happen is an electron may come over here, electrons get injected into the p side here. It may recombine, and again the same thing. Note that electron comes here, it recombines. Electron hole pair is generated here, and the electron comes over here. So in the external circuit, in the wires and all that, of course, current flows through electrons. But inside, the current may flow because of holes going from P to N, electrons going from N to P. So that kind of a process occurs. So there's an injection process and there's recombination. Current flows through injection and recombination. Holes get injected into the N-type, recombine here. Electrons get injected into the P-type, recombine here. And so injection and recombination is occurring. And in the external circuit, we saw what happens here, resulting in a current that flows there. So that's forward bias. That's how current flows. In simple terms, that's how current flows here. And we also said that when you apply a bias here, the electric field gets reduced. The electric field gets reduced here, and therefore the depletion region narrows. And depletion region narrows. So what happens is, note that the charge here, there is a negative charge here, there's a positive charge here. The charge has changed. And anytime, so application of forward bias reduces the depletion width. And note that because of the change in charge due to voltage here, we have a capacitance here. So anytime there is charge there in the device and it changes with the voltage, you have a capacitance. Del Q by del V is capacitance here. And so we found that when we applied a voltage here, the charge reduces here, the charge reduces here, and therefore there's a change in charge in this region in response to capacitance. So PN junctions have a capacitance in them. There's a capacitance between P and N region because of this particular phenomena here. There is also capacitance because of other things. Note that we said that P region, what is happening is holes are getting injected into the N region, electrons are getting injected into the P region here. So note that this is the concentration of excess holes because the holes come into this here. So there are excess holes in this region here. There are excess electrons in this particular region here. Again, there are charges. The holes carry positive charge, electrons carry negative charge here. So there are charges, and these charges change as a function of voltage. So that also gives rise to capacitances here. And we call that capacitance as a diffusion capacitance. So anyway, we'll not get into the details of all of these things, but the point is that inside the PN junction, within the PN junction between P and N, there are capacitances that are there here. And the origin of those capacitances is depletion charge. The origin of those capacitances is also the charges that have been injected from P to N and N to P. And they give rise to capacitances in a PN junction. Let's look at reverse bias. So in a reverse bias, again, this is neutral with loss of electrons, lots of holes here. And in equilibrium, the diffusion tendency is balanced by drift tendency here. Now, when we apply in this particular direction, this is going to cause an additional electric field, and the two electric fields will add up with each other here. So the electric field becomes even stronger. Okay. And so now, because of this negative bias here, you would like current to flow from left to right. Right? That's the direction of the current that the battery would require a current to flow in. And so basically, for holes, the holes have to flow from left to right to give rise to a current like this, to contribute to current. And electrons have to flow from, the holes have to flow from right to left, and the electrons have to flow from left to right to contribute to current in this direction because electrons carry negative charge. So let's look at this. You are asking holes to flow from right to left. So you're asking holes to flow from N to P. And how many holes are there? Very few. Very, very few holes are there, and it's for that reason that very little current will come, because very little current would flow. To contribute to current flow in this direction, the holes have to go from N to P, and there are very few holes in the N region here. Similarly, to contribute to electron current, the electron current has to flow from P to N, and there are very few electrons in this particular region here. So the problem is that in the reverse bias direction, you are asking holes and electrons to flow in the wrong direction. From N to P for electrons, and from N to P for holes, and from P to N for electrons. And there are very few such carriers in this particular region here, right? The movement of carriers from N to P is, for a hole to move from, let's say, N to P is not difficult, because note that the direction of the electric field in this direction here. So in a hole which comes here, we'll see an electric field which will push it to this particular direction here. Similarly, an electron which enters the depletion region here, we'll see this electric field, the electric field will push it here. So the problem is not in terms of crossing this particular region here. The problem is there are very few holes here, and there are very few electrons here, right? And so because of very few electrons in P-type and holes in N-type, the current is very, very small. So that's the reason why we get very little current in the reverse bias direction here. Now, application of reverse bias increases the potential inside the junction here, because we just said that the electric field becomes stronger. There's an internal electric field, and then when you apply a negative bias, it adds to this particular field. So the field becomes stronger, and therefore the potential becomes higher here. So earlier, this was VBI, the potential in the junction here. Now, when you add a reverse bias here, the potential in the junction becomes VBI plus VR here. And the depletion region, because the electric field becomes stronger, so the earlier the depletion region was between these black dotted lines. Now the depletion region becomes larger here. There's red dotted lines here. So there's more charge in the junction here. Again, note that there's a change in charge with voltage here, so there's a capacitance associated with it. All right, so that was the qualitative operation of PN junction. So let's look at then the relationship between current and voltage. So the current and voltage are related through this exponential relationship. I equal to Is, exponent, Vd is the voltage across, N Vt minus 1. Vt is what we call as the thermal voltage, Kt by Q is K Boltzmann constant, T in Kelvin, and Q of course is the charge, and the value of this is 26 millivolt at 300 Kelvin. At any other temperature, you can of course substitute the temperature and calculate what is Vt. N is what we call as the ideality factor, and if N is equal to 1, we call such diodes as, we call ideality factor equal to 1, or we call such diodes as ideal diodes, N equal to 1 here. Okay, in practical diodes, N could be 1, often N is somewhere between 1 and 2. And Is, we call it as the reverse saturation current. So if you're going to analyze circuits using PN junction diode, so this is the model of the PN junction diode. The current and the voltage are related through this exponential relationship. So in forward bias, when Vd is positive, so what happens is Vd is positive, and most of the time we are applying voltages which may be much larger than 26 millivolt here. So we've assumed a ideal diode N equal to 1. So Vd is much larger than Vt, so this exponential is much larger than 1. So in forward bias, we normally write the diode as I equal to Is exponent Vd by Vt. And if we plot it out, or if we take log of this, so log of I is log of Is plus Vd by Vt. So if I plot the IV characteristics of a PN junction diode on a log scale, on a semi-log scale here. So this is log and this is linear, right? This is linear, voltage is in linear scale, and this is in the log scale here. So this is the practical diode 1N4001. Okay, so diodes have, there are all kinds of, there are hundreds or even thousands of different kinds of diodes that are available, and each one of them will have a particular number attached to them, and will have their own unique characteristics. So 1N4001, if we were to take this particular diode, measure its IV characteristics, plot it on a log scale here and linear scale here, this is how it looks. And so what we are trying to show you here is that if it were an ideal diode behaving this kind of an equation, then ln I will be equal to ln Is plus Vd by Vt. So an exponential on a log linear plot would have looked like a linear line, a straight line here, which you see here. So 1N4001 in this region here, it obeys like a ideal diode here. Okay, almost like an ideal diode, we obtain, this linear equation is there. But as you go to lower bias here, well, it departs from that kind of a behavior. It's no longer exponential. There are other things that are happening inside the diode here. Similarly, if I go to higher biases also, you may begin to see that the curve starts bending here. The curve starts bending here. It's no longer exponential like this here. So there's a range of voltage and range of current over which any practical diode would behave like a pure exponential characteristic. If you go to higher biases or if you go to very lower biases, it will no longer be an exponential curve. So that's something that we need to be aware of. When we are using a diode, if we are in this particular region or we are in this particular region, it may not obey this simple exponential characteristics. But if we are in this particular region, then it obeys the exponential relationships that we are talking about. Now, it may have n equal to 1 or it may have n equal to some other value here. but it's a exponential characteristic. So there's a range of voltage, range of current over which a practical diode has exponential characteristics. Go to very low voltages or higher voltages here, it's no longer this simple graph here. Note that what does lower voltages mean? Well, in this case, you can begin to see that maybe less than 0.3 volt or so. What does higher mean? Maybe more than 0.8 volt or so here, right? So lower and higher depends on the kind of diode that we're talking about. For silicon diodes, maybe greater than 0.8 or so, it's no longer exponential. These, putting numbers, because there are all kinds of different diodes, so quoting a single number is problematic. But you can see here less than 0.3 or so. Again, it is not exponential here. The other thing that you note here is that we normally keep on saying that the diode, there is a current flowing at all voltages. There's a current flowing at 0.1, 0.2, 0.3, 0.4, at all these voltages that are there. So it's not that diode conducts current only after a certain voltage. For example, you may read somewhere that PN junction diodes have a cut-in voltage, that below cut-in voltage the current is 0 and above cut-in voltage the current is significant. But this is the real characteristics of a diode here. Note that the current is always flowing, and whether the current is significant or non-significant depends on your application. And so if you say that current above, let's say 10 milliamperes, this is 10 milliamperes, so above 10 milliamperes is significant, that above 10 milliamperes is significant, then what you're saying is that you have to apply a voltage maybe more than 0.7 volt here, or around 0.7 volt here. If you say that maybe current of 1 milliampere or 0.1 milliamperes is significant, then you're talking about 0.6 volt here. All right, so depending on the current of interest, depending on the nature of the diode, the voltage across the diode that is there, of course it varies. The voltage across the diode, you can see here, the voltage across the diode depends on the current that you are passing through the diode, and depends on the nature of the diode, depends on the saturation current of the diode. In the reverse bias case, we have this equation here. And if you apply a reverse bias VD equal to minus VR, and you're applying, let's say, a significant reverse bias, say minus 1 volt or minus 0.5 volt or so, this quantity then becomes negligible here. And so I becomes equal to minus IS. And so therefore, that's the reason why we call this IS as the reverse saturation current. So what we say is that when you apply a reverse bias, the current is constant. Note IS is a constant. It doesn't depend on the voltage anymore. So that's why, and it's the reverse current. So that's why we call it as the reverse saturation current here. And so reverse saturation current is difficult to see in this particular diagram because both the forward current and reverse currents are plotted on the same scale, and the reverse current is much smaller here. And that's the reason why you cannot see this reverse saturation current. Now, what would be a typical value is hard to quote a typical value. It could be 1 picoamperes. It could be, maybe in nanoamperes. It depends on the nature of the diode again that we're talking about. Also note that the actual current that is flowing in the reverse bias direction may be much higher than this value that you see here. And because of, again, the actual practical diodes are more complicated, as we indicated, more complicated than this particular equation here. There's another problem in reverse bias, that here we are showing that reverse bias current is constant and is equal to reverse saturation current, but only up to a point. If you keep on applying higher and higher reverse bias voltages here, what would happen is eventually a phenomena called breakdown occurs, and the diode starts carrying a large amount of current. The diode can conduct large amount of current, and we say that a breakdown has occurred in the diode here. So note that diode will conduct very little current in the reverse bias only if the voltage is less than the breakdown voltage. If you get close to breakdown voltage or beyond, then the diode can conduct very large current here. And the reasons for it are, for example, there's a phenomena called impact ionization. So the idea is, note that when you're applying larger and larger voltage in the reverse bias direction, you're creating larger and larger electric field in the reverse bias direction. And so the idea is that then you may cause a process called impact ionization, a phenomena called impact ionization. So for example, note that what may happen is when you see an electron like this, and let's say electric field is in this direction here from right to left. And if the electric field is high, as this electron moves, it gains energy from the electric field. And as it gains energy from the electric field, what it may do is it may ionize the lattice. It may knock an electron hole pair. So as it moves from here to here, the electron gains energy from the field, and it has enough energy to liberate an electron from the conduction band to from the valence band to the conduction band, and thereby create an electron hole pair. Now, this electron may start moving and gain enough energy, and it may cause impact ionization also. So, so note that earlier there was one electron which was going from left to right here, but now because of impact ionization, you get now two electrons here, or three electrons here. And now these electrons can further move and cause impact ionization. And these holes can move and cause impact ionization. So the point is that note that current is because of electron and hole pairs. So the point is, even though you may have very little initially reverse current, an electron flowing from left to right, if the field is large, that one single electron can create many electrons and holes there. And one single hole can create many different electron hole pairs. And that's the reason why we get lots of current if the field goes beyond a certain point, or in other words, if the breakdown occurs here. So note that in reverse bias condition, the holes are flowing from N to P, and there were very few holes moving from N to P, or electrons were going from P to N, and there were very few electrons. But because of impact ionization, now, even though one electron entered, you got two electrons, two moved, they cause impact ionization, 4 occurs, and this hole moves out, these holes move out. They may cause further impact ionization. So what we are looking at is a multiplication process which is occurring. A single electron may enter your depletion region, and through impact ionization may create many electron hole pairs, and those electron and hole pairs will create further electron hole pairs, and there's a multiplication process occurring if the field is sufficiently large, and then you get very high current even in the reverse bias direction here. So this process is what we call as this multiplication process is what we call as the avalanche breakdown here. Avalanche, like in the mountains, it occurs. It may start off with a little bit of snow falling down, and then it gathers more snow, and eventually you find all this big mass of snow coming down here. So similar process is occurring here. One electron may enter, and then it may knock out one more electron. Those two electrons may knock out further two more electrons, and you get 4 electrons, and there's a multiplication process occurring, and you may end up getting large number of electrons, then eventually exiting and coming out on the N side, and similarly large number of holes coming out from the P side here, and you get very large current here. So this breakdown is what we call as the avalanche breakdown. And there's a separate phenomena also that can occur is ionization can also occur where the electric field it's not a multiplication process, but similar to avalanche, the electric field may simply, it's not one electron gaining enough energy from the field and knocking out an electron hole pair. It's simply an ionization process where large electric field rips an electron out from the lattice here, right? So large electric field ripping, something similar to breakdown that may occur, let's say, between two plates, an electric arc kind of a thing here. Okay, so that's a different breakdown mechanism in the sense that an electron is not gaining energy from the field and knocking out an electron hole pair. That was called impact ionization. This is what we call as field ionization. Both are due to fields, but a different mechanism is there. In this case, the electric field is so large that an electron simply you break a bond and you create an electron in a hole, and you break a bond, you create an electron hole, you break a bond and you create an electron hole. So if the electric field is so large that you start breaking up and you causing these ionizations, so you get a lot of electrons and a lot of holes, and again a very large current begins to flow here. So we call this process as a Zener breakdown, and often it occurs in very heavily doped junction here. So all this is field ionization is occurring here. Okay. So electric field breaks the bond, creating electron hole pairs. These are again very simple pictures to illustrate what may be happening inside the junction here. So most of the common PN junction diodes that you will encounter, they will break down due to avalanche mechanism. All right, so okay, so let's stop here.